Our today's topic is one-way ANOVA. It is nothing but the abbreviation of analysis of variance. This technique is basically used when you want to compare several means with respect to mostly with more than two, basically. So, for example, we want to compare a mean HbA1c, which is observed in percentages among hypertensive, normotensive, and hypertensive group. So we have one continuous variable and we have one more variable with three categories. Like for example, here our variable is like we want to compare our outcome variable with three categories. So one variable is about, for example, the tension levels. It has three categories: hypotensive, normotensive, hypertensive. And our outcome variable or our response variable is numeric. Usually we observe the HbA1c in percentages. So in this case, when we have one numeric variable and when we have one categorical variable with more than two category, and we want to compare the means of that outcome variable, that numeric variable, then we use the technique which is called as ANOVA, or which is anything but analysis of variance. To work on the ANOVA, we have major three assumptions. One is independence, that each observation is independent of other observation. Like we are obtaining the observation from single person or one individual separately. Then one more assumption is normality. Okay, because our outcome variable is a continuous variable, so we have to check the normality of that variable within each group. Like if we are considering the same example of comparing the HbA1c between hypertensive, normotensive, and the hypertensive group, then we have to check whether the HbA1c is normally distributed within a normotensive, within hypotensive, and uh, within hypertensive. Then this will be checked by the Shapiro-Wilk test or Kolmogorov-Smirnov test based on the sample size. Usually we use Shapiro-Wilk test because of the small sample size we have. Then we have one more assumption is homogeneity of variance. It is basically it does not directly affect the ANOVA, but when we have to run the advanced analysis, we have to consider this assumption. That is, the variance in each group, variance within each group are equal to the other group. So it will be checked by the Levene's test. In ANOVA, we have certain steps of hypothesis, like our null hypothesis is that all the means are equal, all the means of the outcome variable within each group are equal. And null hypothesis this time is not simply that mu1 is not equal to mu2 is not equal to mu3. This time we have the alternative hypothesis that at least one of the mean is not equal in any category. The step number two is level of significance, which is alpha, as defined by the investigator. If it is not given, we take 0.05. Test statistics this time we have one way ANOVA because we are comparing several means of our outcome variable, and then provided that the assumption of normality is fulfilled. And then we have the critical region, which is nothing but the rejection region. We will reject the null hypothesis that all the means are equal if the p-value which we obtain from the data will be less than equal to alpha. Computation is described in the next slide, and result conclusion depends on the nature of the problem. To understand the empirical application of ANOVA, we have this example. The data which is given here, it represents the number of hours relieved by the 5 different brands of headache tablets that administered to 25 subjects experiences fever 38 degrees centigrade or more. So perform the analysis of variance, test the hypothesis at the 0.05 level of significance that the mean number of hours of relief provided by the tablet is the same for all 5 brands. So these are the 5 brands, for example, brand A, brand B, brand C, brand D, and brand E. And these are the 25, 5 observation in each in tablet A, 5 observation who took tablet B, 5 patient who took tablet C, and 5 patient who took tablet D, and 5 patient who took tablet E. So we have two variables here. One is type of tablet. Another variable we have the number of hours relieved by the headache. For example, the patient number 1 was relieved in 5.2 hours. Similarly, patient number 25 relieved on 7.6 hours using brand E. The data is actually entered in this format in SPSS. Like first we enter the data for the A, and these are the coded like 1 for A, 2 for B, 3 for C, 4 for D, and E, 5 for E. And corresponding to each tablets, we note it down to the corresponding time relief, which was given in our example. To proceed for ANOVA, first we have to check the normality because it is the first of the main assumption. And we have two tests. One is Shapiro-Wilk test, and another one is Kolmogorov-Smirnov test. We are going to the Shapiro-Wilk test because of our small sample size. So it can be checked by using the option in SPSS like analyze, compare, mean, explore. In the explore, we will provide. I mean, we will transfer time relief in the dependent list, which is our response variable, and a continuous variable. In the in the factor list, we will provide that value as tablets because it is one thing is that we have to check the normality of each brand, and also it is a categorical variable. Then we click on this plot option. In the plot, we have the option normality plot with test. Once we click it, we out of several table and the graph, we have to seek the table which says test of normality. In the test of normality, we can see the sig is the p-value, and all the p-values in this case are more than 0.05, which implies that we can proceed to the one-way ANOVA if any one of the p-value would be less than 0.05. For example, let's suppose for the brand E, the p-value would be 0.047. We cannot proceed to one parametric one-way ANOVA. So under this and null hypothesis that the overlay follow a normal distribution, so we can accept the null hypothesis that all that the time relief hours in all the brands of the tablets follows normal distribution. So now we'll proceed to our main example, which is about the 5 tablets, and we will start with the hypothesis that the 5 brands have the same mean time relief, and at least one of the mean is not equal. It's an alternate hypothesis. Alpha was defined by the researcher, which we took alpha is equal to 0.05. Tested since our time relief also follows a normal distribution, and we have to check the mean of the 5 groups. We are going to apply one-way ANOVA, and we will reject the null hypothesis p-value as an alpha. To proceed towards the ANOVA, we will go to the again analyze option. Then we have option of compare mean, and then one-way ANOVA. Once we click on the one-way ANOVA, it asks two things. One is the dependent list, which is time relief in our case. And then we have the factor, which is the brands of headaches. We have A, B, C, D, which is coded one. Not the string. It won't accept the string variable. So when we run the analysis and we see this table in the output file, and this is nothing but the p-value. Wherever you find the physics in the software, this is nothing but the p-value, and this p-value is less than 0.05. It implies that the mean number of hours a day provided by the tablet is not same for all 5 brands, or you can also say at least one of the tablets did not produce the same time relief as the other one. We also we also have to understand how to check the variance assumption, that is a homoscedasticity or homogeneity of variance. This will the Levene test will help us to check out, and this we can approach using the ANOVA option. So again, we will go to the using the same option, analyze, compare between one-way ANOVA. In the one-way ANOVA, we have this button, which is option. This option have the test by homogeneity of variance test. We will click on it and we will press continue, and it will produce this table other than the ANOVA. And in ANOVA, since we were actually working with the null hypothesis that the variances of are same in all group, So this sig is more than 0.05, 0.706. That means that the time relief or the variance of the time relief hour within each group are equal. This is for today. Next time we are going to study post hoc analysis.